Hello. We are uh, from the challenging team for the project base. My colleague Petrovac, I'm Martin Mulap. So we perform this challenge with the help of our mentors, and let us begin. So we are evaluating physical consistency of machine learning model outputs. Uh, the first question is why, and why does it matter? As most of us know, the machine learning in weather prediction is increasingly popular, and it is gathering many success stories, and it's very efficient in what it's doing. Excuse me. However, the limitations are that there are usually no physical constraints to the outputs. So we would like to examine and evaluate how physically consistent the outputs actually are. We would like to pinpoint some inaccuracies and improve reliability of those models using such tools. We are focusing on multivariate physical consistency. So most of the metrics are using more than one field to cross-examine. So some single variates might be missing, but those can be implemented later. So we are focusing on uh, uh, some of the present, like geostrophic balance, hydrostatic balance, cross-variable correlations, and so forth. Uh, okay, so the workflow is basically dependent on the config file, which user can modify freely, choosing from either prepared datasets or configuring own new dataset. Uh, and then some reference dataset, which is supposed to be from traditional numerical prediction system. You can also choose some spatial or temporal slices, and then also the diagnostics that you would like to compute. From that, the dataset is initialized, the modules are computed, the outputs are gathered. We are using PyTorch as our backend, and the outputs are stored inside the ZAR archive for efficient storage and efficient use for later post-processing. We also have some post-processing modules implemented, but again, those can be added later or externally on the outputs. So why did we choose PyTorch? Because it basically required us to implement a few things over all of the things from scratch, but it provides a few advantages. Uh, the first one is that it can be directly used during the optimization of the models that acts as a physical sort constraint or physical regularization, improving the models in this area. And also, it helps us to understand the mysterious AI output uh, as can be shown using some tools using the backwards differentiation. So let me pass colleague now.
So for our evaluation, we have used a combination of machine learning forecasts with physics-based references. First, we have GraphCast model, which is from Google DreamMind. It operates on the 2.0.25 degrees resolution, or it has variables on 37 pressure levels. And we use this as a main model for evaluation for metrics like geostrophic and hydrostatic balance and others. Next, we have a coordinate dataset, which is sort of a high resolution machine learning downstream forecast. It operates on 2 kilometer resolution, but it has only limited surface variables, all in 2 meter temperature, 10 meter wind gas, and 6 hour precipitation. We have therefore used the model parametry for case studies evaluation. And as physics-based references to benchmark these models, we have used an R5 p-analysis as well as Cosmo p-analysis too. So these datasets enable us to evaluate both large-scale dynamics as well as small-scale processes. So moving on to the results, first we have geostrophic balance. So we computed by deriving the geostrophic wind on geopotential gradients, and we compare it to the actual model wind. And we can quantify the measure of imbalance by the ratio of geostrophic wind ratio to ratio. Then we plot this ratio using histograms and graphical profiles. Here we have shown 5 different model lead times for the gapcast, and the dash line is error 5. So you can see that the deviations increase with increase in lead time, which suggests degrading physical consistency. Looking at the spatial patterns, we can see that some features are smoothed out, for example here and here, and also some special patterns appear, although these are probably caused by numerical errors, not the actual physics. Next, we have hyperstatic balance, where we compute this by comparing the vertical geopotential difference from the actual data and the one computed from the virtual temperature. And we quantify the difference between these two by the absolute and relative errors. So we again plot this for 5 different lead times for the GraphCast with the reference error 5, and we again see that the deviations increase with increasing lead time. So next we have humidity temperature consistency, where we basically compute the relative humidity using the Clausius-Clapeyron relationship, which we can see that it is most generally maintained, although we can see a notable difference, which is this spike, which appears only in error 5 data, and this spike corresponds to clouds, which GraphCast obviously misses. Next, we will look at the potential of vortice inconsistency, where we also can see the special pattern, the special patterns which are generally consistent, although we can see some deviations with increasing lead time. As for the mass and energy conservation, we also plot these using time series. You can see that they are generally consistent only about after 5 days. Some deviations appear. Another important check is cost variable correlations. You can use these diagnostics whenever a machine learning model has at least 2 outputs. So here we look at the U and V components of the bins. So you can see with the orange one is the error 5, and some deviations appear again with the outcast. And similarly, the correlation errors on this spot increase with lead time. So another way to check cost variable relationship is using bivariate histograms. So here we have the Golding model. This was actually in the event of the occurrence of the cold front. So here we compare the 2-liter temperature and total precipitation, and we can see that the GraphCast model, the Kirby model predicts temperature, precipitation at the higher temperature, which may highlight some inconsistency. And we also have conducted some case studies using the Kirby model. So first we had cold front. So we can see that the precipitation is generally well aligned with the temperature gradient. So the Kirby model represents the frontal passage well, although the temperature gradient is slightly smoother and the precipitation is underestimated. We have also looked at other individual ensemble members, but they were very close to the mean. Then we have large-scale convection. We can again see that the Kirby model represents the large-scale convection quite well. The gases are perfectly positioned ahead of the leading edge of the system, and precipitation is slightly behind. We can also see on the southern flank. Here we can actually put it like this. You can see increased gas and as well precipitation, which was actually not present in the ground truth data, so that highlights the model's ability to capture physical consistency. Last, we have small-scale convection, and here we compare the 2 ensemble members. So on the left, the first member missed the event entirely. It collects precipitation without associated wind gas, which are typically present in this kind of event. But on the other hand, the other member collected precipitation and with wind gas quite well, although the storms were not as isolated as on the ground truth data. So to summarize the diagnostic results, we have seen that the physical balance is great for yield time. For the geostrophic and hydrostatic balance, it pulls after 2 to 3 days. For mass and energy, it pulls after about 5 days. And regarding the dynamic consistency, it was mostly maintained, although we have seen that missing one other that's on the relative humidity spike. And it also variable correlations were mostly realistic. And we are seeing that probably captures large scale events well, but small scale convection remains challenging. However, we should handle knocking.
Okay, so some of the impacts of these projects are that we can use it to guide model development, either through interpretation of the results or through direct optimization using those diagnostics, and thus build trust and interpretability of the machine learning models, which is now lacking. It is also open source and ready for APC use. We are also considering implementing it compatible with cloud usage, but that remains to be done. Some of the limitations are some sensitivity to the input data. So, for example, if another data set with different resolution would be introduced, some changes in the pre-processing would be necessary, and also some fixes in the diagnostic modules, and also some post-processing as smoothing of the large scale of the small scale features isn't necessary to be adjusted for those. Also, some limitations of compatible data is present. So, for example, it assumes that you have a multivariate output as it was intended for TCUs mostly. Some of the future work include quality of life improvements to have it more flexible, as mentioned in the cloud, or generally more less codey, so to speak. And also, we would like to add option to use it directly on the model inference or direct optimization. So the dataset handling would be omitted. We would also like to develop some dashboards with easy and understandable visualizations that can be configured or directly accessed. Also, for the diagnostic and computation part, we would like to refine the diagnostic modules for increased accuracy and robustness to different data. For example, better handling of vertical derivatives or boundary conditions. Also, we would like to introduce some additional metrics, also single variate, so that it would be all in one package without needing to use another modules for different metrics, and then scale or make the post-processing module more scalable, as currently this was done as a single process operation. So that is all from our side. Thank you for attending.
Gracia, Peter, and Martin, are there any questions? You have what? Yes.
Yeah, Nick, guys did a great presentation. There's also a really nice set of metrics that a lot of people there are interested in, especially when it comes to verifying the physical consistency of morely machine learning model. My first question is like, what the output there? Yeah, we're package take this out this next sub files to shoot up.
The inputs are netcdf files, but for the features, the intention is also to have it compatible with tar files, but it can be modified. The code is not that heavy.
Just asked it to see how size we can adapt it to our machine learning concept in the cloud wiki and the AI access. And my second question is, this is for deterministic forecast, so like one forecast.
Currently, yeah. For Cordif, we had ensemble outputs, but we did not have yet enough time to make it compatible. But some of the thoughts were to have it compatible with something like Anovo in datasets format, which has the ensemble dimension.
Yeah, that's really cool. Would be really interesting to see also like to adapt and see if there are some members that are more unphysical than others. Actually. Oh yeah, thank you again.
Good. Okay, well, yeah. Yeah.
Did you look at
you look at whether the more physical models or the more physically consistent models are actually more skillful, if there is a correlation, or if that there is no real correlation. They're just wrong in another way.
Well, that's a very tricky question, which I will answer in a tricky way also. So we had basically two types of diagnostic modules. Either the one that compared to some reference. So for example, the broadcast was always compared to ERA5, which it was trained against. And the other type of diagnostic is just within the outputs, where you have no reference as itself, but you can pull some. You could definitely apply it to the physical models and see if they behave well, but then it's difficult to determine what is the baseline or what's the target.
We have just looked at the Gapcast model, so its evaluation, but it would be interesting to see also other models.
Okay, then Niels, please.
You call the deviation from parastatic just only balance an arrow, but I mean that's okay. A single gives sports kit. And did you take it into account in your diagnostics? Like did you do temporal and spatial averaging over large skates to see the
Yeah, so the idea was to evaluate this compared to the FN dataset ERA5, and we said this dataset is physically consistent. So everything that is different from ERA5 is inconsistent. And if the errors are actually increasing, that may suggest that the consistency is breaking. So that's how we evaluate things.
ERA5 is also a direction sort of the Nobel path, so it's not necessarily. I mean, I think that the map might get better as you take it out for smoothing horizontally and averaging.
For the geostrophic balance, now smoothing was present. It was basically just the decreasing the resolution. But yeah, like the interpretation is not that easy in Italian.
Good. Another question? Okay, then another round at the top.
So
Hello from Baltimore already. Okay.
Hi.
So yeah, you will introduce the your team in the project, Mickey.
Yeah, so this year the data sources proposed a challenge called ML Coughing, which is involved with trying to predict from a request, from a data store request, um, a dictionary, how long is it going to actually take to execute while it starts to execute us. So we had a team of 5 participants from France and Luxembourg, namely Dak, Viet, Wu, Nat, and T. We did not really use names of these ones, but yes, the participants kind of achieved the goal. The challenge maybe was a bit ill-formed because we did not took in consideration that the same request done at different times in the data flows might take a different amount of time. But yeah, the basic managed to predict the best value possible over how long the request is going to take. I'll leave it to, I guess, Viet. Is that it?